Good evening, everyone. Let's wait for a few more minutes. Okay. So this is the last session, and this is the extra session. So what I'll do is give few problems on superconductivity, maybe one more, and then I'll move to a overall problems, basically MCQ problems from the whole topics randomly, and some problems might get repeated. So whichever I may have solved in one of those sessions. Okay. Okay, so this is the first question. An external magnetic field H is applied to a type 1 superconductor at temperature below the transition point. Then which one of the following statement is not true for H less than the critical field Hc? So the first option is the sample is diamagnetic. Second is its magnetization varies linearly with H. Third is the lines of magnetic induction are pushed away from the sample, and the last option is the sample exhibits a mixed state of magnetism near the Hc critical field. So solve this problem, and then there is nothing to solve in this question, just an option. There might be some noise background, please ignore it during this puja sessions.
Sir, I think option D, sir. Not true means.
Right. Hmm. Okay, so the sample is below critical field, right? Sample is below critical field. Below critical field means it is still superconductor. If it is superconductor, then it is diamagnetic, right? So first option is correct. If it is diamagnetic, then it will repulse the magnetic induction lines. So third option is also correct. Now, it magnetization varies linearly with H. Now this is where the type 1 part comes in. Okay, so for type 1 superconductor, chi is proportional to m, actually minus m, because okay, so no, this is not true. So m is proportional to minus h, and from this we can say that chi equal to m by h equal to minus 1, that is diamagnetic. So option B is also correct. So the only option incorrect is this mixed state of magnetism. Mixed state means it is diamagnetism and paramagnetism or ferromagnetism mixed state. Okay, so this is the correct answer according to this question, because we need to find the false uh, false part. Sorry. Okay, so again we need to find the false statement. So first option is type 1 superconductor is completely diamagnetic. Type 2 superconductor shows Meissner effect up to the second critical magnetic field. Third option is type 2 superconductor exhibit zero resistance up to the second critical magnetic field. And the last option is both type 1 and type 2 superconductor exhibit sharp fall in resistance below Tc.
Sir, option C or D, sir?
Option B is correct. See, zero resistance means in experiment you can never achieve that zero resistance. It is kind of becomes beyond measurement. So the measurement instrument has some capacity or some limiting, that precision limitation limit, right? And in superconductor, what happens below the transition temperature? It drops so sharply and it almost becomes zero. That doesn't mean ki it is exactly zero. So we cannot measure that very low resistance with our measurement system. If we increase the precision by some means, then maybe we will be able to measure. So why second option is correct? Because if we see the magnetization versus applied magnetic field curve for type 1 and type 2, so this will be M. So this is type 1 and this is type 2. Okay. So for type 1, below the critical field it goes like this only. Okay, so this is Hc. That means this region is superconductor Sc, and this is minus M. So what happens for type 2 is that it is also like somewhat like type 1, but then after a certain magnetic field it starts decreasing, but there is no sharp decrease like this one. Okay, so it gradually decreases, and the linear portion for the linear portion the field is hc1, and whenever it becomes 0, exactly almost 0, then we call it hc2, second critical field. So for this portion, that is linear m minus m versus h behavior, the chi is exactly -1, right? So it is perfectly diamagnetic for both the type 1 and type 2. But beyond hc1, this portion chi is less than -1, mod chi, let's say. So that means, okay, so not less than, it will, so mod chi will be greater than 1, mod chi. So this will mean that m by h, so some magnetization will be there, so that the flux, so flux start, so initially it was like that, flux lines do not enter the superconductor, but after this hc1 they start penetrating the sample. Okay, so that means perfect Meissner effect is not there for type 2 superconductor. Okay, up to hc1 this is okay, but beyond hc1 the Meissner effect start decreasing. So this option is wrong. Okay, so this is the correct answer then. Okay, so let me move to other problems.
Sir, I have one doubt, sir.
Mm-hmm.
I think type 2 superconductor also having the Meissner effect and the Silfi effect, sir.
No, type,
Type 1 is perfectly Meissner effect,
right.
perfectly pure diamagnetic.
Hmm.
But
Hmm.
type 2 also some book mention it Meissner effect.
No, no, there is perfect Meissner effect in type 2 as well, as long as you are below TC, sorry, HC1. Okay, so below HC1, if you are in type 2, then perfect Meissner effect. So up to HC1, type 1 and type 2 is equivalent. There is no such difference. But beyond HC1, the flux spinning gets destroyed slowly. So that means, so the what is the option? So type 2 superconductor shows Meissner effect up to the second critical magnetic field. So this is
Okay,
partially
okay,
true.
sir.
Okay, so this is partially true. This statement is not correct totally. If you talk about option C, then type 2 superconductor exhibits zero resistance. That is actually true, because up to Hc2 the resistance is so negligible that we can call it a zero resistance. In fact, if it is not zero, significant resistance is there, then we will not call it superconductor above Hc1, like we have not called type 1 superconductor beyond Hc1, right? Okay, so the question is, consider a crystal containing a paramagnetic impurity whose energy levels are plus epsilon and minus epsilon in a given magnetic field. Now, the specific heat at high temperature will be proportional to T to the power minus 2 T cube, T to the power square, and T to the power minus 3. Which one of these are correct? Is correct.
You can explain, sir.
So we need to find the specific heat. Specific heat contribution due to that paramagnetic impurity. I'll solve the problem. Let me wait for a few minutes if anyone solves. So anyone solving? Okay, so let me solve it. So we need to find specific heat. So specific heat CV, one of the way to get it is that du dt, where U is the internal energy and T is just Kelvin temperature. So we need to find U, right? But okay, so yeah, so we need to find internal energy, and internal energy we can find out by having that partition function. This is a concept of statistical mechanics. So partition function in the classical limit, or let's say Maxwell-Boltzmann statistics. So this is according to Maxwell-Boltzmann equation. It is e to the power minus beta epsilon I. That's it. So epsilon I is the all the energy, all the possible energy levels, all possible energy levels, and I goes to let's start from 1 to n. So if there is n levels, then it will go to up to n. So we have two energy levels. One is minus epsilon, one is plus epsilon, right? So then in this case, z will be e to the power minus epsilon for this one, beta epsilon basically. Beta is 1 by kbt, and then plus e to the power minus beta of minus epsilon, right? So to the power plus beta epsilon plus e to the power minus beta epsilon. So this is the partition function, and this we can easily say that this is 2 cos hyperbolic beta epsilon. Okay, and the internal energy, the relation with partition function is d ln z by d beta. So derivative of log of z with respect to beta. So this will be 1 by z and del z del beta, right? So if you find this derivative carefully, then it will be minus epsilon tan hyperbolic beta epsilon. Then we can find Cv. Cv equal to du dt. Instead of beta, here it is derivative of t. So if you do this, then you'll find that Cv will comes out to be beta epsilon square sec hyperbolic square, basically beta epsilon. So this is the Cv for all temperature at any arbitrary temperature beta. Now we need to find high temperature condition. So at high temperature, T goes to infinity, right? So then beta goes to 0. So in this limit, Cv will be okay. So in this limit, before that, let's find out the sec hyperbolic. Sec hyperbolic square becomes sec hyperbolic square beta epsilon. In the limit beta goes to 0, it equals to 1. Okay. So then Cv becomes Kb beta epsilon square. That means Kb epsilon square by Kb square T square. So which is proportional to T to the power minus 2. So the first option is correct. Okay. So this is how we can find out Cv. In fact, sometimes we also may ask just find the internal energy at some temperature, at an arbitrary temperature, or in some other limit. So this was for T infinity. There may be question for T tending to 0. Okay, so next question. Okay, so in Landau theory of ferromagnetism, the free energy is given by f of m equal to half of a function of t m square plus 1 by 4 bt. B is basically a function of t m to the power 4, where m is that magnetic moment or magnetization. For non-trivial equilibrium value of m expression is given m equal to plus minus minus at by bt to the power beta. So what is the value of beta? We need to find the beta. Just find the non-trivial solution of m from Fm, non-trivial equilibrium, right? And from there you can see the beta. So anyone found the answer? Okay. So if m is given as half of a t m square plus 1 by 4 btm to the power 4. So for equilibrium, del f of m, del m will be 0, right? This is the extremal condition for f of m. So this will be a of t m plus b of t m cube equal to 0. That means m a of t plus b of t m square equal to 0. So there can be two solutions or three solutions. This is a cubic equation. So one is m equal to 0, and then another two is plus minus Okay, so let me fully solve it. So from this part, m square equal to minus a of t by b of t, right? So then m will be plus minus root of minus a of t by b of t, right? So this is plus minus a of t by b of t to the power beta, where beta equal to half, right? This is the correct answer, half. This is the solution already given. Now notice that we are concerned about non-trivial solution. Non-trivial means non-zero. M equal to non-zero solution. And this is already 0. So that is trivial solution. Okay, so next question. So I'm actually going randomly any question from any topic.
Sir, 12th assignment, first question I have doubt, sir.
12th assignment, first question.
Yeah, I think one value is not given. I think constant value or you put the answer. That's one is I have doubts.
Okay, so let me open that assignment then. That will be helpful. So let me stop sharing this. Okay, so you can see my screen, right?
Yes, sir. Yes, sir.
Uh, so the
Once
first,
again, you can solve it, sir.
so the first question.
Yes, sir.
Assuming the polarizability, that is alpha, I need to find dielectric constant, epsilon. Okay. Just let me write down the question. Okay, so given alpha, we need to find what is the epsilon r or the dielectric constant, right? And this was Kr or argon, whatever atom. So one we have epsilon r minus 1, epsilon r plus 2 equal to n alpha by 3 epsilon 0, right? This is Clausius-Mosotty equation. Now alpha I have n number of atom per unit volume. I do not have. Okay, so if I think from other perspective, the
A
following
solution provided by the NPL team.
what?
Solution already uploaded.
Okay, so in the solution I need n, right? They have given n,
Oh, no, no.
or is there any other way we can find n? Let's see.
Sir, they are using that already solved solution send me, sir.
Hmm.
But they are only Avogadro number dividing by 22.4 into 10 to the power of minus 3. That value is how can come? That one is problem. I think Krypton constant value, sir.
Okay. Right, right. That may be correct because n is material constant, material property. So I need to know the material property for krypton. Okay, so this type of question I think they will avoid in the exam at least, because in the exam I don't have any time to find the n value for krypton and then do the solving the problem, right?
Okay, okay.
Mm.
Sir, please check its final result. There is taken a polarizability
Mm-hmm.
to only two numerical part 2 into 10 to the minus 40. But in question given
Mm-hmm.
2.2 result differs. Actual
Okay.
result not come in the solution.
Okay.
Question, correct option may be option B.
Okay. So options are also pretty close that I have seen, right? 1.006 and then 7, then 8, then 9. That was the case. probably.
Yes. So I think it should be 1007.
Okay. So for that, I need to know the n. But that can anyone tell me what is n that the answer sheet finds?
So 2.68 into 10 to the power of 25 per meter cube. 2.68 into 10 to the power of 25 per meter cube.
Okay, so I am assuming it is correct. Okay. So if I have that, then using this formula, epsilon r minus 1, epsilon r plus 2 equal to alpha is 2.2 into minus 40, 3, 8.85 into 10 to the power minus 12. Let me find. So then epsilon r minus 1 equal to 2.22 10 to the power minus 4 epsilon r plus 2. Okay, so the final answer is around 1.00066, right? So yeah, it is 1.0007 is the best answer. Okay. Okay, so next problem. So related to this polarizability, okay, but that we cannot do anything. Okay, so again, the best way is to approach NPTEL, and they will contact Professor Das and resolve this issue. Okay, even we don't see your assignments as well. So you can raise a complaint or just inform the NPTEL and share the. Okay, how to contact NPTEL? Let me find the email then. Okay, so one option may be, so for ourselves, the TS, there is other email address actually, but that will not work for you. I'm just copying the email address from which I get regular email for the announcement. Okay, so this is the email address, online courses at the rate nptel.itm.ac.in. So we provide the solution, scanned copy of solution, it will be better. Okay, so if the dielectric constant of NaCl crystal is 5.6 and its optical refractive index, or simply the refractive index is 1.5, then find the ratio of its electric polarizability to its total polarizability. So anyone have any idea how do I solve this? So I need to find the ratio of electric versus total polarizability.
Ionic polarization plus atomic polarization by ionic polarization.
Right. So we need to find the ratio of electric by total. Total means electric plus ionic. Okay.
Yes.
Electronic plus ionic rather.
Yes.
Okay. So let me solve it. So again we will use Clausius-Mosotty equation. So this is, let's say, total. Okay. So for total we need the epsilon dielectric constant for total crystal is given as 5.6. So epsilon is 5.6. So then from this equation we can get 5.6 minus 1, 5.6 plus 2 equal to n alpha by 3 epsilon 0. So then n alpha by 3 epsilon 0 will be 0.06, sorry, 605. Now this was total. Now let's find electronic. So electronic, let's say epsilon r minus 1, epsilon r plus 2 equal to n alpha electronic by 3 epsilon 0. Now we have given the optical refractive index n equal to 1.5, right? So optical refractive index primarily contributed by the electrons basically. So then from this refractive index we can find the electronic contribution to the dielectric constant, and the relation between n and epsilon r is that n equal to root over epsilon r. Okay, so root epsilon r is 1.5. That means epsilon r is 2.25. So if we put this, so then n alpha e 3 epsilon 0 will be 0.294. Then the ratio equal to alpha e by alpha, right? Electronic to total. That will be n alpha e by 3 epsilon 0 basically by n alpha by 3 epsilon 0. So 0.294 by 0.605. So that will be around 0.5. Okay, so this is the answer. Okay, so next question. Okay, so this is a problem from Bragg diffraction. The second order maximum at the diffraction in X-rays of zero point 0.2 nanometer wavelength from a simple cubic crystal is found to occur at 30-degree angle to the crystal plane. We need to find the distance between the lattice plane.
Sir, option C.
Correct, option C. So this is straightforward. N equal to 2, theta equal to 30-degree, right? And we know 2d sine theta equal to n lambda. So then 2d sine 30 equal to n equal to 2 and lambda is 0.2 nanometer. So d will be 0.4 nanometer, which is 4 angstrom, right? Okay, so next question. So the low energy electronic excitation or just the dispersion in a two-dimensional sheet of graphene is given by E equal to h bar Vf k. Vf is the velocity of excitation. So we need to find the density of state proportionality, basically proportional to E, that is energy to the power 3 by 2 root over energy, or E square.
Option A.
Right. So how do we find this?
Derivation. I think three-dimensional means e power minus 1 by 2. Two-dimensional e power 1 and one-dimensional e power.
No, we are going reverse actually, but okay. So 3D it is e to the power half, and 2D e to the power 0, and then 1D e to the power minus half. That was for the conventional parabolic dispersion. Parabolic means epsilon or energy is h square k square by 2m, right? So for this type of dispersion, 3D, okay, let me write DOS. DOS means density of state. DOS proportional to root epsilon. 2D for this kind of dispersion, DOS is proportional to e to the power 0, and in 1D it is proportional to e to the power minus half. So this was for the parabolic. Now the dispersion relation itself changes, h bar vfk. So now how do I find DOS proportionality basically? So the answer is correct. It is proportional to energy, but how do I find this? That I want to know.
You can explain, sir.
Okay. Okay. So DOS is simply DNDE, right? So this is the most primitive definition. N is the number of state. So then DNDE basically represents the number of state within the energy range DE, right? So it depends on the dimensionality, obviously, from this set of expression. So in 2D, we can easily find out, we easily find by this analogy basically. So let's say we have a two circle concentric. Okay. So this is not concentric, but assume this is concentric. Okay. So this is suppose K, and this is K plus delta K. To find the number of states between these DE energy range, so we actually, what we actually do is that GE DE, or equivalently GK DK. GK is the this part, GED or G equivalently GKDK gives the number of states, rather total number of states. Okay, if we divide by the energy range, then I will get DOS. And this GKDK is usually happens L by 2 pi to the power D. L is the dimension of sample, which is constant, and then So I'm giving the generic expression and then I'll solve for this 2D case, okay. So elementary K space
Actually,
J.
sir, in this case,
Mhm.
n proportional to k to the power 3.
In this case, n is proportional to k to the power
That
3. Okay,
this is
so if I go by
massless.
your words, then n is proportional to k to the power 3. Okay, so
But
essence.
dn by d then k square. dn by de uh, consequently
So if
comes with
n is proportional to k cube, then it is also proportional to e cube, right? Because e is simply h bar vf
yes,
k. So then dn
yes.
de will be 3e square. That means it is proportional to k square. But okay, so we need this part only. So this should be proportional to e square.
It is for sir. It is for
Mhm.
massless direct system. Massless direct system.
Not really. So let me find out, and if you have any doubt, ask me. Okay, so the generic expression or to find the number of state is that L by 2 pi to the power d, and then elementary area in K space. Okay. Now this is still you can use in 3D or 2D. If I specifically come to this 2D case, then what will be this elementary idea? This annular portion, right? So the elementary area will be d of pi k square equal to 2 pi k. Dk means delta k, right? Delta k. This part is delta k. This portion. This is delta k, right? You can actually find another way. Okay, so this is being congested. So pi of k plus delta k square minus this is straightforward k square. Now we can find this will be 2 pi k delta k when we ignore delta k square equal to 0. Delta k is already very small, so delta k square will be more small. So this will be around 2 pi k delta k. So then this is L by 2 pi to the power d, and then for 2d it will be 2 pi k delta k, right? So n, sorry, DOS we need to find. So DOS is gk, and gk is proportional to this part, right? Gk, dk and delta k are equivalent basically, okay? So when we take infinitesimal element, then dk and delta k almost we treat equivalently. So then gk is proportional to 2 pi k, and gk is the DOS, right? So this was the total number of states. Gk dk was the total number of states. So then DOS will be gk dk by dk, or if we talk about energy, then GEDE by DE. This is DOS. So both expressions are correct. If you are doing in K space, then this will be useful, and in the energy space, this is useful. So DOS is proportional to K means DOS is proportional to energy. Okay. So for massless Dirac system or that 2D graphene which have been considered here, this is massless Dirac system. So DOS is actually proportional to E, not E cube or E square that you are saying. Okay, so option A is correct.
Actually, sir, I told in three-dimensional case.
Okay, that may be. So let me actually find out. I also don't know this 3D case. So in 3D, what will happen? D of G of k dk will be proportional to 4 by 3 pi k cube. So this will be proportional to 4 pi k square dk, right? 4 pi k square is the spherical area and then dk, extension of that. So then gk, which is DOS, is proportional to k square. So if it's k square, then e square. That's right. Right. True. Okay. So next problem. So this is the general way. Okay. So don't remember in that way. If it is parabolic, then this is the way, and then for the linear, that is graphene, this will be the case. For 2D, energy proportional. For 3D, energy square. So the best way is to find this. This is the general formula. Okay. And how do I find elementary area? Elementary area, just D of that area. Area in 2D will be simply, okay, so this is actually misleading. This is elementary area or volume for 3D, or elementary line element for 1D. This is 1D, this is 2D, and this is 3D, right? Okay. So obtain the Miller indices of a plane having 2a, 3b by 2 and infinity on the crystallographic axis. Okay, so having intercepts basically. Uh, so 620, that means 310 basically, right? No, not 310. 310 is not correct answer. So anyone else? Right, 340. So we find Miller indices simply like A by the intercepts on the A corresponding axis 2A, and then B by 3B by 2, and then C by infinity. Right, A, B, C are the lattice constant along the respective x, y, z direction, let's say. So this will come out to half 2 by 3 and 0. So which is 340, right? So this is the Miller indices. So silicon has a diamond structure with unit cell edge 0.542 nanometer. Need to find interatomic separation. Oh, the correct option is 0.383, option C. Okay, so let me solve it. So diamond diamond actually have FCC structure, okay, face centered cubic. Now for face centered cubic, if r is the radius of atoms, then 4r equal to corner of a edge, not the corner of the whole cubic, corner of a face, a root 2. So if I draw this, okay, so let's focus on this face. So the front face, then in the face centered cubic, the atoms are like that. So, okay, so in the face, if I only see the this front face, then it will look like a square where there is some circular atom. Okay, so again some circular atom. All atom actually have same radius, but it is not evident from my drawing. But anyway, so this is r, this is 2r, this is again r, right? And this is a, this is a. So that means the total diagonal will be a root 2. This is what I have written. 4r equal to a root 2. And we have given a unit cell edge. And we need to find the interatomic distance. So interatomic distance is this one, right? Center to center. So interatomic distance d equal to 2r equal to a root 2 by 2. So that means 0.542 into root 2 by 2 nanometer. It will be 0.383 nanometer. Okay, so this is the correct answer. C. Okay, so next question. So the density of NaCl is 2189 kg per meter cube. It forms FCC crystal. So we need to find the lattice constant. So anyone solve this?
Sir, 5.61.
Right, 5.61. Okay, so need to find lattice constant. But what we know is that density, formula for density is Nm by Na a cube, right? N is the number of atoms in the unit cell, m is the molecular mass, and then Na is the Avogadro number. So we need to find a so a cube equal to Nm by Na rho. N is 4 for FCC and M for NaCl is 58.5.
Sir, your voice is not audible, sir.
Okay,
I think mute.
okay, sorry. So right, so the density formula is Nm by Na cube, where N is the number of atom in the unit cell, M is the molecular mass, and then A is the unit cell dimension. So we need to find A. N is 4 for this FCC crystal, M for NaCl is 58.5 in SI unit. So we have and then rho is given as 2189. So then finally A will be 5.61 angstrom, right? Okay, so next question. So what is the total void volume? Void means there is no atoms in that volume for gold at 27 degrees Celsius, making hard sphere approximation in the calculation. Okay, so for context, gold is again FCC structure. Okay.
Sir, I think A option.
So the void volume is no, not A.
Sir, atomic packing factor 74%, na, remaining 26% M2. What formula using, sir?
That's true. So okay, so we need to find the void volume, not the packing fraction. Right, and it should be in the semi-cube per mole. Whatever you have said is correct in the percentage. So for that, actually, the question doesn't give that information, but you need that actually. So molar volume for gold is 10.3. Sorry, volume it is semi-cube per mole. Okay, so this is not given, but you need that. So for FCC, you can directly say that 75% is the occupancy factor, right, or packing fraction. Packing fraction. So remaining 25%, remaining 25% is the void. Almost 75%. So the void volume. So this is only true for FCC, by the way, right? So void volume equal to 25% means 0.25 into the molar volume 10.3, which will be around 2.68 semi-cube per mole. Okay, so option D is correct. So the radius of the Fermi sphere of free electrons in a monovalent metal with an FCC structure in which volume of the unit cell is given a cube. We need to find that radius of the Fermi sphere. So which of this following option is correct? So anyone found the answer? Okay, let me solve it. So you have given a monovalent metal with an FCC structure, right? So FCC structure means n equal to 4. Monovalent means one electron contributes to the valence electron. And we need to find the radius of Fermi sphere. So radius of Fermi sphere is what? Or rather Kf, Fermi function, or the Fermi sphere we use in the K space. So we know the Fermi energy expression is given by h bar square by 2m 3 pi square n okay, so there is a confusion in the notation. So let's call it capital
2
N,
by 3.
number of atoms. So this is 1 2 by 3, which is h square by 2m 3 pi square capital N by v 2 by 3, right? And this expression we can equate with conventional parabolic dispersion h square kf square by 2m. So that means kf is 3 pi square capital N by v to the power 1/3, right? So this will be 3 pi square. N is 4. There are 4 atoms, and into 1, because monovalent, that means one electron contributes to the valence electron. And then volume is a cube to the power 1 by 3. So that means 12 by 12 pi square by a cube to the power 1 by 3. Okay. So option A is the correct answer. So this is the radius of Fermi sphere. Okay, so this was the last question of this session, including all the sessions. Basically, today is the last session. So yeah, so I hope I have been able to deliver something meaningful throughout this course, TA sessions, and there are a lot of problems that we can do into we could have done in this today's session, because I have barely touched all the topics. Probably not. Okay, so not possible in a 2 hour session. Okay, so when is your exam? I mean, exam date.
Sunday,
Okay, so
29.
next Sunday.
29, sir.
Okay, so the question pattern probably you know. So everything will be said by Professor Das, and he will oversee this, and also the exam will going to be proctored, right? There are few online software as well as there will be manpower. So I think the best way to prepare is to go through the assignment solution and the assignments, how each problem is being solved or are being solved. That is the most important part, because Professor Das have prepared that assignment questions, and he will set the final exam paper. So while we think, so we have solved the problems which are by and large in falls with those topics, but immediate questions and answers that Professor Das likes to give, that he knows the best, right? So the best is to go through all the assignments and assignment solution once again, understand how each of these problem are being solved, and what are the underlying fundamental concept behind those questions, right? So if you prepare this very well, you are almost set for the exam. After this, if you have time, then come to each individual TA sessions PDF notes. You start from any of the TA which you think that most relevant his or her TA sessions was. So again, go through the notes and see how each problem are being attacked and what are the types of problem. So that is the main uh, thing that you can do in this short time. Don't read anything very new which you have never read. The point being, in exam there is a little bit of stress always works, and this is very easy to forget the thing that you have uh, recently read. Even if you don't forget, the chances that you will remember half or one third of that, not fully. So the best is to retain all the concepts that you have acquired throughout the coursework, rather than embarking on something new totally. Okay, so that was kind of advice or suggestion from my side. Someone raised a hand. Yes, Madhu, what is your question? Hello. So do you have any question? Okay, so anyone have any question, or else I'll end the meeting. Okay. Thank you for joining. Best of luck for the exam. So I'm ending the meeting. Okay.
Thank you, sir. Thank you.
Yeah. Thank you.